So today, we're going to dive into a concept that is absolutely fundamental to so much of our world, from how your microwave heats up food to the very chemistry of life itself. We're talking about the electric dipole. Let's break down exactly what it is, piece by piece. Here's the game plan. We'll kick things off with the basic definition. What are we even talking about? Then we'll figure out how to calculate the electric field it creates in a couple of key spots. After that, we'll put our knowledge to the test with a real-world problem. And we'll wrap it all up with a handy summary of the formulas you'll want to remember. All right, let's get right into it. First things first, what exactly is an electric dipole? When you boil it all down, an electric dipole is actually super simple. It's just a pair of point charges. That's it. The only rules are they have to have the exact same amount of charge, but opposite signs. So one is plus q, the other is minus q. And they're separated by some small fixed distance. We call that distance 2a, and there's a good reason for that, which we'll see in a second. This diagram here shows the setup perfectly. Now, the key thing to notice is how it's labeled. The total distance between the charges is 2a, and we do that just for convenience, really. It lets us put the center of the dipole right at our origin point, which means the distance from the middle to each charge is just a. Trust me, this little trick is going to make all our math so much cleaner down the road. Okay, so we know what a dipole is. Now for the fun part. What kind of electric field does it create? We're going to start with the simplest case, finding the field at a point that's sitting right on the line that connects the two charges. We call this the dipole axis. To find the total field out there at some point P, you can't just look at the dipole as one thing. You have to consider the field from each charge all on its own. And the most important thing to remember is that electric fields are vectors. They have a strength, sure, but they also have a direction. So the positive charge creates a field pushing away from it, while the negative charge creates a field pulling towards it. The total field is what you get when you add those two opposing vectors up. This whole process has a fancy name, the superposition principle, but don't let that intimidate you. All it really means is that the charges don't mess with each other's fields. We can just calculate the field from the positive charge, like the negative one isn't even there, then do the same for the negative charge, and finally just add the two results together to get our final answer. Simple as that. So how do we do it? Well, we take Coulomb's law, that's our basic recipe for the electric field from any point charge, and we use it twice. Once for our positive charge and once for our negative one. Then we do that vector addition we were just talking about. Yeah, there's a little bit of algebra involved, but when the dust settles, we get this nice exact formula that tells us the electric field at any point along that axis. But here's where things get really, really cool. If you move far away from the dipole, those two opposite charges start to kind of cancel each other out. And that big complicated formula, it simplifies a lot. And it reveals something profound. The dipole's field strength drops off with the cube of the distance. That is way faster than the field from a single charge, which only drops off with the square of the distance. This rapid decay is the unique signature of a dipole. All right, let's switch things up. What happens if we're not on the axes anymore? What if we look at a point that's on a line that cuts right through the middle of the dipole, at a perfect 90-degree angle? This is what we call the equatorial plane. And this is where symmetry becomes our best friend. Check it out. At any point P on that equator line, the distance to the positive charge is exactly the same as the distance to the negative charge. Now look at the field vectors. See how the upward part from the positive charge is perfectly canceled out by the downward part from the negative charge? They just vanish. All you're left with are the horizontal bits, which are both pointing in the same direction, so they add up. The math totally backs this up, but it also gives us a new, really important idea, the dipole moment, which we represent with the vector p. Just think of p as a little arrow that captures the dipole's whole identity. Its length is the charge q times the separation 2a, and by convention, it always points from the negative charge to the positive one. And here's the interesting part. On the equatorial plane, the electric field actually points in the exact opposite direction of this dipole moment vector. And you guessed it, just like in the axial case, when we get far away from the dipoles, the exact formula simplifies beautifully. And look at that. Once again, the electric field strength falls off as 1 over the distance cubed. This 1 over r cubed relationship is the telltale sign that you're looking at a dipole field. All right, theory is great, but let's make this stuff real. We're going to apply our brand new formulas to solve an actual numerical problem. This is really where the rubber meets the road, and these ideas start to click. Okay, so here's our setup. We've got two charges, a plus and minus 10 microcoulombs, and they're separated by 5 millimeters. Our mission, should we choose to accept it, is to find the electric field at two different spots, P and Q. Both are 15 centimeters away from the center, but one is on the axis and the other is on the equatorial plane. So, for point P on the axis, it's a simple three-step process. First, we need to calculate the dipole moment, P. Remember, that's just the charge times the distance between them. Step 2, since our point P, which is 15 centimeters away, is way farther than the 5 millimeters separation, we can totally use that simpler far-field approximation formula. Then, step 3 is easy. Just plug in the numbers and crunch it out.
And we get an electric field of 2.7 times 10 to the 5 newtons per coulomb, pointing right along the axis.
Now let's tackle point Q, out on the equatorial plane. The process is pretty much the same. Step 1, we already did it. We have our dipole moment P. So for step 2, we just need to grab the right formula. This time, the approximation for the equatorial plane. And for step 3, we plug in the same values as before and see what we get. The field at point Q works out to be 1.33 times 10 to the 5 newtons per coulomb. Now, hold on a second, take a look at that number. It is almost exactly half the strength of the field at the axial point P. And that is precisely what our formulas told us would happen. One formula had a 2 in it, the other didn't. It's so cool when the theory actually works. So, to wrap everything up, let's pull all of our key results together in one place. You can think of this as your go-to toolkit for solving any problem that involves an electric dipole. This table lays it all out for you. We've got the formulas for a point on the axis and a point on the equatorial plane. And for each spot, you've got the exact formula that works no matter what, and then you have that much simpler approximation that's a lifesaver whenever you're far away from the dipole. So why do we care so much about all of this? I mean, why is it so important? Because this isn't just about abstract equations on a page. This physics is happening everywhere, all around us, and inside of us. Take the water molecule. It's a permanent electric dipole. And that one simple fact is the reason it's such an incredible solvent, the reason it forms hydrogen bonds, and the reason it enables the very chemical reactions that make life possible. It really makes you stop and think, doesn't it? How different would our entire world be without this simple little arrangement of two opposite charges?